All right, I think we are live. We're going? I think we're going here. All right, hello, welcome. This is our week 7 live session for the IBM Data Analytics Bootcamp. Uh, in the States, we just had a long weekend, so either way, I hope you had a good, relaxing weekend. And hopefully, we can get some more folks here for the next class. But yeah, my name is Alexander Booth. I am the head program instructor and head facilitator for the IBM Data Analytics course. As you all know, Keith had the original instructor for this, had a kind of medical emergency just after a couple weeks in the boot camp, so had to step away, and I've been in since about week 5, week 6 or so, and will take us to the finish line. So I had a great time last week talking about SQL in week 6. In week 7 here, we are moving into what I like to call exploratory data analysis. It's our EDA week, but note that this week does a lot more than that. It's a pretty heavy week in terms of content. We're going to be moving from extracting data from databases, wrangling it, doing feature engineering, preparing that data essentially for modeling, exploration, and downstream consumption. And then we'll walk through how to explore the data, look at various data distributions, look at the shape of data, try and understand patterns, skew, correlations, etc. In the second half of lecture and in the second half of the week, we're going to be tackling introduction to machine learning, is what I like to call it, our intro to predictive analytics. We'll be creating linear models, essentially our line of best fit, creating that linear regression, and then interpreting how good these models are. It's a good foundation for advanced modeling concepts that, I'll probably talk about in weeks 9 and 10 during the capstone work. So it should be a fun week. I definitely have some content to go over, some notebooks, and we'll go over the quiz, the week 7 quiz as well. One quick piece of information before we get going. Last week's session is already posted on Zoom, and if you're in our official IBM Data Analytics class and forums, you can access the Zoom links directly. But I also have the lecture backed up on my YouTube, as well as a kind of recap of week 6, preview of week 7. That's up there as well. And then finally, I'm also backlogging a few lectures. So I actually just posted the week 5 live session, just again as kind of a back recorded session since I know Keith was out for that one too. I'm also going to do a week 4 back recorded live session as well. So I guess not live session, but lecture. I'll do a back recorded lecture for week 4. So you should have through Keith, hopefully, I think he did weeks 1 and 2. Then you'll have live sessions like this from me for weeks 6 through 10. And then I'll have a couple back recorded lectures that I still am recording like live. Like I'm not just uploading like old things. Like I'm recording them live for you. So you'll have that for at least weeks 4 and week 5. And then I'll check with the facilitators about week 3. I'm not sure if anyone recorded that or not, but if I have time, maybe I'll just go back and do it too. Why not? All right. So, like I mentioned, we have 4 more live sessions scheduled here, taking us into the middle of June. We have week 8 is going to be all about data visualization, business intelligence, and interactive dashboard design. Pretty good week. And then we move straight into the capstone. So, expect more capstone talk to come up as we get into week 9 here, going into early June. All right, so let's start going through our media sets. Like I said, the big idea for week 7 is exploratory data analysis, moving from data wrangling and pre-processing to data distribution exploration, pattern identifying, outlier research, and then moving into predictive modeling using linear regression. It's a pretty good week. Let's see. I think the discussion forum doesn't come about until pretty later on. So let's just kind of go through some of the media sets here. I think I only have time to run a couple of notebooks, but you never know. If I get bored, I may run through 3 here just to kind of get this to an hour. All right. Cool. So again, big ideas. We're going to be ingesting data into Python and then manipulating and interacting that. So kind of a deep dive into pandas as well. Again, as we're exploring data, if we want to be real data analysts, you can't just be data analysts in a vacuum. You have to really understand the underlying data set. That gives you what we call domain expertise in the space. And that domain expertise is important as you start trying to identify what is right, what is wrong, what could be better in the data set. So we're going to start with some basic data exploration here in our media sets. So looking at the data types, looking at null values, looking at .info. We've talked a lot in week 6 and week 7 of how to connect to databases. That's going to be a very common data source for our data analytic workflows, as well as a destination. I don't think we're going to do this first, a notebook. Like I mentioned, I've already run all these notebooks. If you are running any of them, feel free to check against my GitHub, and you should see that I have everything backed up here. Whoops, that is the wrong location. Where are we? Module 7. There we go. So pretty good stuff here. You'll see that, again, the first couple notebooks are all about acquiring data, reading them into data frames, and then exploring those data frames, right? Looking at the head, the tail, fixing our columns, all of that good stuff, null values, etc. Let's keep moving on into the next activity here. Again, none of the practice quizzes or the media set notebooks are actually have to be done. The only thing that's graded each week is the week 7 quiz, or is the weekly quizzes. All right. Oh, there we go. We jumped straight into the discussion forums. So let's have a quick look at that. So the week 7 discussion forums, there's like a few different ones this week. Oh yeah, there's 4 different posts. So again, if you're in the forums, you want to engage with us, would be great. I've dropped a couple of just thought-provoking questions that I put in there over the weekend. So you'll see things like what I think about when we think about pivotal and like libraries and takeaways for data exploration. We want to look at data manipulation. We want to look at feature engineering, numerical computations, and then visualization as well. I added some of my favorite pandas functions here and how pandas works with SQL, as well as just some additional context around special characters, delimiters, all of that good stuff. Basically, all the problems in data, especially if you're reading them from flat files and flat CSVs. Again, so if you have thoughts on this, feel free to participate in the forums. Pre-processing. Here we go. This is one of my favorite sections here. So this could be like literally a whole week just on pre-processing and cleaning data. But I think it's some good starting points here. When we have a data set, before we can trust it or use it for intelligence, visualization, or even like agentic AI, it needs to be clean and ready to go, right? So we call that step pre-processing or data wrangling. And you'll see that some of the big ideas here is dealing with missing values. Common strategies for that include dropping the missing rows, which is typically fine if your data set, if your missing rows or columns are a small percentage of your overall data set. But the other option is replace the missing values. This is known as imputation in data analytics. So you usually replace the missing value with either the average, the median, or the most frequent value. So that's the mode. All of those are good ways to impute missing values. And we'll do that later today as well. Let's see, other things to do, feature engineering, basically creating new columns, standardizing columns. So in this case, we're creating new columns based off of units. And then data normalization, especially when we get into linear modeling and basic predictive modeling, what you'll see here is that range matters a lot. So we call this like, yeah, your mean, median, mode, and range. Your range or your variation. If I have 2 columns, one is age, goes from 0 to 100, the other is income, goes from 0 to 1 million. Those are vastly different ranges. And when there is increased range, increased variance in the data set, sometimes linear models get biased towards those larger numbers, right? So the idea between standardization and normalization, we want to put everything on similar ranges, which typically allows a stronger signal to be developed, especially from those features that may have a smaller range or lower variance. Other feature engineering topics, binning, how do we go from a number into a category? And then vice versa, how do we go from categories back into numbers? Again, when we're building models and things or taking averages, we only can do that on numerical data sets. So we need to encode our categorical features into some kind of number. So that's a good video, brings in, introduces the idea of one-hot encoding, which allows you to encode your categories as zeros and ones, which removes any bias, which is great. So in a common like approach for both of these, let's say that, yeah, I use age as an example for that. So age goes from like 0 to 100 or whatever, but usually we have bins of ages, like age groups, age bins, 0 to 18, 19 to 30, 30 to 40, 40 to 50, 50 plus, whatever, right? So a common use case is take your raw age, bend those raw ages into categories, and then use one-hot encoding to turn those categories into numerical features for linear modeling. I know it's a lot of work, but you're doing great. Thanks for keeping up. All right, so let's actually look at, I want to look at one of these notebooks. This is 7.3, I think. Yeah, data wrangling. So let's look at the last one here. This should be the practice data wrangling. So we're going to be working with a laptop data set here. Let's do it. So let's actually spin up our notebook. Again, what we're doing here is we're using the IBM lab environment to run these notebooks. So cool. You'll see that I ran one of these recently while I was testing it out before the live session. So let's go ahead and clear our outputs, and we should be able to go ahead and just run the notebook. So what we're going to be doing here, we're going to be trying to do a lot of data cleaning and data pre-processing, which is a pivotal step before any EDA or modeling work. So let's go ahead and work through this. Let's import our libraries and go fetch our data. This may take a hot sec for our compute to warm up. There it goes. Awesome. Sweet. So we should have a data set now. Yep, we have this laptops.csv data. So this is what it looks like. We should have all of this work here. It looks clean and beautiful in our browser, but let's see if it actually is. Let's go ahead and read in the CSV into a pandas data frame, which is done. So now we can start doing some exploratory analysis of the health of the data. By calling .info here, we can see a few things. First, the data set has 13 columns and 238 rows. Second thing I'm going to look at is null values. For null values, we see that all of them have zero, a lot of them have zero non-nulls. So zero null values, I guess. They're all not null. So for example, how you would read this. Manufacturer has 238 not null values. And since there's only 238 rows, that implies that every row has a manufacturer. Contrast that to screen size and weight, which are each missing 4 values and 5 values, respectively. So we do have some missing data that we need to figure out. Do we drop the rows? Do we impute them? We'll have to deal with that downstream. The second thing I look at is the data types. So again, typically for us, we want to look and work with numerical data sets. And we have two categories here. So we have manufacturer and screen. And if I take a look at the data set, I think both of those are correct. I'm looking at the data types. They are both strings. But what's really interesting is that they both seem to be categories. They're not just open text, right? Like the manufacturer will either be Lenovo, Asus, Dell, and screen will be full HD or IPS panel. So we have some encoding that we can do to turn those into numerical features, whether it's one-hot encoding or ordinal encoding. Everything else looks pretty good though. I also like looking at column names. It looks like we could probably get rid of this first column or rename it to be something useful. The rest of these, you could probably lowercase them, but they're probably fine. Basically, I'm trying to remove spaces and foreign characters from the column names. Again, we already can preview what the data looks like. And again, we're grabbing the shape of the data here. So it looks like we are looking at missing values, data types, column names. We have null values in screen size and weight. Data types look pretty good, and we're missing a column name, but for the most part, they look pretty good here. I know we can also do some work, including like rounding our screen size. So let's go ahead and do that as well, just cleaning up that numeric feature. And actually, what you'll see in our exploration here, maybe think about it. Do you think screen size is a continuous variable, or do you think it's more of a discrete category? we'll figure that out later in the notebook. All right, so as we already talked about here, we should have five missing values for weight and four for screen size. And we're going to work with imputation. So again, my bias is mostly that if you're less than 5% of rows are null, then drop the rows. That's just my own personal heuristic. But in our case here, we're going to end up imputing them. So let's take a quick look at our data sets here. I'm going to look at the weight column first. These are the five rows where weight is null, and all the rest of the rows look pretty good. So the argument to not drop these rows is that there is useful information here because it's only the weight that's wrong, right? So why are we dropping all of these other potential signals just because the weight is null? So for imputation here, this is going to be a numeric continuous feature. So we're going to be filling it in with either the average or the median. So let's do a quick check. There's no skew in my data set. The average and the median are approximately the same size, so it doesn't matter which one we use. I'm going to end up using the average here. But just also for proof of concept, this is only 2% of all rows. So if you do decide to drop these rows, no one's going to hold it against you. All right, so let's start imputation here. What I'm doing is I'm grabbing the average weight of a laptop, and then I'm replacing the null values with that average weight. And now if I try and filter my data frame, you'll see that there are no rows where the weight is null. Hooray. And if I look at one of the rows here, you'll see that we've imputed the weight with that average, that 1.8622 value. Cool. All right, now let's look at screen size. Screen size, we're going to look at the average and the median. There is a little bit of skew here. We'll see that we do have our median higher than the mean. So the average screen size is a little bit smaller. So we maybe have some phones or something that bled its way into the data set. But this is really interesting. If I actually look at the value counts, you'll see that screen size is a discrete variable. It is not continuous. That we have like 89 laptops that are all approximately 39.62 in size. And this is going to be pretty common across the board for laptops. You'll see that they're going to come in specific discrete screen sizes. Cool. And if I look at the mode here is going to be that 39.62. That is the most frequent. So that's kind of what we're doing. We're grabbing the mode, and then we're going to replace the null values with that mode. So if all goes well, we should have replaced them all with 39.62. And if we look at our .info, no more missing values. Hooray. Last couple things that we're doing here. We can confirm that these new columns are all floats, which they already are, but whatever, we can just double check. And then the second one is I'm fixing my column names. I'm going to rename this unnamed 0 column, and I'm just going to rename it to ID. So that just makes it a little bit more descriptive of what we're doing here. Cool. So we got a clean data frame now, and let's work on some of the other standardization and feature engineering work. So honestly, when you've cleaned the data like this, you could probably hand it off to BI or whatever. But let's say we do want to start feeding this into linear models. We need to start feature engineering and preparing our data set for that analysis. So some of the feature engineering work we're going to do, because we're running from a point of view of an analyst in the Western Hemisphere, or in the United States, I guess, we're going to convert all of these units into imperial. So we're going to convert kilograms to pounds and centimeters to inch. I already hear everybody overseas crying out in frustration, crying out in standard units. Oh, yeah, I get it. I get it. But whatever, just for the sake of this example, we've standardized and changed our units. Let's also look at that idea of standardization, or like why normalization matters, right? So if we look at, I'm going to call this df.describe here. This allows me to look at the max and min, which is the range, right, for all of my numeric features. And see, a lot of these are fairly close, right? Category, GPU, CPU frequency, they all go from like 1 all the way up to like 20 or something. But if we look at downstream, we can see that the storage gigabytes is a pretty large range from 128 to 256. And then the price obviously also has a long range. Typically, you wouldn't normalize your target. So in this case, if we're trying to predict price, you wouldn't normalize it. But we may do it here just for sake of example. But one thing we can definitely normalize is the storage, right? We can normalize that down to get into that 0 to 1 or -5 to 5 range that all of our other columns seem to be in. All right, so let's go ahead and look at some distribution charts. Again, this is looking at the shape of U, the shape of the distribution. What does the shape of this individual column look like? So what I'm looking at here is the shape of the price distribution, and we can see that we're pretty right skewed, right? We have a few laptops that are all over $3,000, which is biasing the rest of this feature set or this column. Our median is more so like along here, but our average is being skewed and pulled higher because of these. So and that's another use case for normalization is that it reduces the effect of that skew in those outliers to an extent, not always, but it reduces the noise that those outliers and skew can give a model. Same thing with CPU frequency. We'll see that we're actually bimodal here. We have kind of this mini peak around 1.75 and another one around 2.5. But again, like we could probably standardize this down to reduce some of the bias that this implies in the data. So we're just going to do this is a quick and dirty standardization. Essentially, this is what's called like a min-max. So I'm going to be standardizing CPU frequency from 0 to 1. It still should keep the same shape of data, but it's reducing the range of it into a range that should carry more signal. So yeah, there we go. We've squished it down to be between 0 and 1. And there's actually libraries to do this. We recommend using the standard scalar function inside of scikit-learn. So again, I wouldn't recommend scaling price as a target, but for example, we can normalize price to be in its z-scores, which again crushes it down to about a -5 to 5 range. So we should be hopefully looking at that same histogram here in a second. There we go. So that's kind of well, we can actually get the full histogram, right? I'm gonna try running this one as well. Why not? How do I insert a new cell? There we go. Plop that in, plop that in. What do we call it? Price scaled. Sweet. So you see, yeah, we've squished everything. It goes down to about -2 to 4. But yeah, if it did have some left skew, that would shove it out to like -5. So even though we do have these outliers, they fall within 3 standard deviations of the mean. And again, the idea here is if we look at our dot describe, we should all be fairly standardized now in terms of our scales. Probably we could look at scaling storage, but maybe that's an exercise for the reader. All right, let's keep going with some other engineering wrangling tasks. So we talked about binning as well. Binning is where we take a number and turn it into a category. So we're going to do that for price. We're going to take the raw price and we're going to turn it into low, medium, and high categories. And again, we'll see here are our cutoffs. Anything less than 527 or 527 to 1621 is a low price. 1622 to 2715 is a medium price. 2715 to 3810 is a high price. And we can actually make a bar chart and we can see that a majority of our laptops are low to medium. And it's only those real outliers that are this high price here. Now let's go from categorical to numeric. So let's look at one-hot encoding. So again, we looked at manufacturer a little bit earlier. We have about 10 or so here, maybe a dozen individual manufacturers. We can actually turn them into a matrix of zeros and ones using one-hot encoding. Pandas has a built-in one called get dummies, but scikit-learn also has a one-hot encoder for more robust machine learning pipelines. We take a run here, we'll see kind of what this looks like. It's basically transposes the manufacturer into a sparse matrix. Ooh, so many buzzwords in this lecture. But yeah, you'll see like in row 0, right? The manufacturer was Acer. So it gets a 1, all the rest of them are zeros. Row 2 had a Dell. So that one gets a 1, all the others are zeros, etc., etc. So every row should have one guaranteed 1. So we're gonna end up doing this for our IPS panel or for our screen type as well as for our manufacturer. And we can see kind of what this looks like after we've encoded both of them. So again, all I've done here is encode our manufacturer as well as our screen type. So you see we have 2 columns now For screen, that's either going to be a one or a zero, and then same thing for manufacturer. But what I should look at this again, ignoring price. Assume price is my target, so we can ignore these other two columns. Everything now is numeric, right? I either have an integer or a decimal for every single column, which means we can start pumping them through machine learning algorithms, linear modeling algorithms, and actually start looking at plots, looking for correlations, looking at patterns to start identifying predictive modeling capabilities. All right, and that completes the lab. So really good stuff here. I'm going to download this so we can back it up to our live session notebook. And let's pop back on over to our media sets here. Another fun discussion post. So this will be the 7.4 discussion. Let's take a quick look at that. Yeah, so for the 7.4 discussion, again, this is deep into data wrangling and pre-processing. Like, what are the challenges? When would you need to use normalization or binning? Again, I like to push you on these questions. I really think that the data foundation is core to being a good data analyst. You're not going to be able to create your BI tools, your ML models, your downstream consumption. Garbage in, garbage out, right? If you have a bad data layout, then you're going to have bad downstream use cases for it. So yeah, I put my own thoughts in here. Like again, what are the basic things that I look at? Null values, inconsistent formatting, data types, standardizing, and dropping duplicates and stuff. And yeah, cleaning data isn't just a rote technical step. It does require judgment and domain expertise into where the data is coming from and how the data is going to be used and what it means, actually. All right, let's keep flying along here. We only have one media set on exploratory data analysis, but do know that everything we're doing, to me, like the pre-processing and the model development, that all comes from, uh, that all is part of exploratory data analysis. So definitely pay attention to some of these videos here. Again, what we want to uncover with EDA, we want to not just summarize and understand the data, but we want to uncover relationships and extract variables. I also like to put in here, like understanding the limitations of your data. Like, where is your data bad? How does your data not answer questions? That's like, what's wrong with your data, right? Data sets aren't perfect, and if you can figure out the limitations of your data, as well as limitations of models and AI agents and things, that's also part of a real deep data understanding. If you just go out there pitching that everything just works perfectly and answers every question under the sun, you're not going to be really driving like realistic business value. We got some more videos about the data distribution. So we've already looked at histograms and kernel density estimations, but we can also rope into that box plots, violin plots, etc. Again, we're looking for outliers. We're looking for skew. We're looking for weird stuff in the data that could bias or introduce noise. A good concept to keep in the back of your mind is this idea of signal versus noise. What is actually important? What's actually going to be driving decision making? What is signal versus what's biased, what's irrelevant, what's skewing the data and the interpretations? That is going to be your noise, right? So how do you find signal out of the noise? And then once you do have your numeric features kind of ready to go, how do we start looking for relationships between them? In the statistical sense, for data analysts, we use correlation as our big word of the day for identifying patterns. Basically, if one feature increases, does another feature correspondingly increase or decrease in conjunction? So you'll see here that we're going to be looking at cars. Is there a relationship between engine size and price? Not only can we create a scatter plot to look at that relationship, but we can also put in our line of best fit, right? And that's kind of where we're going to tie into in the next couple sections with model development, as well as looking at correlations. So as you can see here, closer to one is a positive relationship, close to -1 is a negative relationship. Either way, there's still signal there, right? Knowing that something goes up when something else goes down is signal. And the only way that correlations really don't mean much is when there is no relationship. And again, if you think about building a predictive model, if you're trying to build a prediction to predict something, but your features have zero correlation or no relationship with that target, then your model's going to be bad, right? Again, garbage in, garbage out. So you want to have good data, a good, strong understanding of the patterns and relationships in the data before feeding it to the predictive algorithms downstream. A friendly reminder that the enrichment activities these are like yeah, these are our notebooks here. I don't think we need to do either of these. I kind of want to jump straight into the capstone, I think, or the keynote for the week, just because the keynote does a good job of tying everything together. But just real quick, let's look at that laptops data again. I'll just scroll through a notebook that I already ran. Here's one I created earlier. So again, same data set. We're looking at the same laptops. You'll see that if I try to look at a relationship between CPU and price, this is my scatter plot, and it's got a fairly weak correlation, right? It's got a fairly weak pattern here. The price doesn't really go up based on the CPU usage. I have some really cheap laptops relatively with high CPUs, and also on the flip side, high price laptops with lower CPU frequency. Same thing with screen size. It doesn't really correlate that well either. Neither does weight. And let's actually looking at some of the distributions here. So I'm looking at the, I guess, the category of laptop. And again, this is looking at the distribution. So we've grouped by category. We're looking for outliers. Definitely do see some outliers here. For category one laptops, we got two outliers with a really, really high price, even though the average of category one laptops are about 50% of that. So maybe we could do some work. Maybe those are misclassified and should actually be category five laptops, which seem to be more expensive in general. This is a pretty interesting one. Number of GPUs. This does seem to have some positive correlation. The laptops with two or even three GPUs seem to be more expensive. I would say these are flagged as outliers, but are probably realistic. Again, that's the other outlier analysis that we do here. Are outliers true or real outliers, or are they just misclassifications? So again, looking at all the shape of data, looking for outliers, looking for data distributions, all of these look pretty good. Again, we can do some more leaderboards, some more aggregations. I think we're trying to look at some correlations now. And again, looking at correlation of price here. Um, yeah, we're correlating the price. We see that they're all fairly low, right? I think RAM is the biggest one with a correlation of zero point 0.5. That's probably the best that we got here. Yeah, CPUs 0.45. Yeah, GPUs didn't even really move the needle either, probably because of sample size. So really, the only features we got that are useful is RAM. So maybe we'll see how we can use that for modeling downstream. All right, let's keep grinding through the media sets here just to get to our live session big notebook. All right, so next we're going to pivot into kind of these last two units here, Unit 4, Unit 5. This is all going to be on creating linear models off of this, right? So hopefully you have some concept of creating a line of best fit, y equals mx plus b. But even if you don't, these videos will walk you through a lot of it, right? How can we define some kind of algorithm or some kind of mathematical equation used to predict some downstream target, right? That's going to be our independent and dependent variables. So for example, given the miles per gallon of a car, can we use that to predict its price? We'll go in a little bit deeper into this in weeks 9 and 10 as you start doing some on the capstone. But this is a pretty important section, and again, could also just have been its own week. So definitely take your time with it. There's some really interesting stuff here. Again, we'll try not to throw too much math at you, but just all you need to know with linear models and linear regression. Linear regression specifically, we are predicting a continuous numeric variable or continuous numeric target. With linear models and linear regression, they're always going to be defined by a mathematical equation. So again, for a simple regression like this, we have y equals mx plus b, or the more mathy equation, b naught plus b1 times x1. Um, with linear models, they're pretty easy for computers to do because humans were doing it 500 years ago. and they're pretty robust and easy to explain, right? We can always pull up the equation, plug in the numbers, and go, this is why my model got this prediction. Contrast that to more modern machine learning algorithms, your neural networks, your random forests. There's not really one set equation, and model explainability can be a lot more difficult. So linear models are always a good place to start, especially for their robustness, their ease, their computational efficiency, and their ease of explainability. One other concept to talk about here is understanding how good a model is. So we call that model evaluation. Residuals will be a word you hear a lot this week. Essentially, the residual is the error. You predict one price, but in actuality, the price was something else. That difference is your error or your residual. So everything you're going to hear later on, your mean squared error, your mean absolute error, even R squared to some extent, all of those are based off of residuals as a core metric. All right, definitely follow up on your readings and your videos. And then a little bit of this is pretty good, I guess. Yeah, you'll see that even with R squared, it's based off of residuals. But yeah, let's talk about more advanced modeling techniques. We'll talk about this too in the capstone or in the keynote for the week. So beyond a simple linear regression, which is usually one feature to one target, we can have multi-linear regression, which is multiple features, so miles per gallon and horsepower. All of that's predicting price. That's two features. Your equation becomes y equals b1 x1 plus b2 x2 plus b naught, right? Whatever your constant is. So that's a little bit more complicated, but usually a little bit more robust as well. We get more information from additional features. And then the other one we'll talk about today is polynomial regression. This is where we still maybe have one or two or a handful of features, but we start adding in exponents, your x squared, your x cubed, etc. And we'll actually see that by adding in squares and cubes, we actually do capture more signal as well. We can capture some more nonlinear effects as we start adding curves and things to our mathematical equations. We already talked a little bit about residuals and R squareds and visualizations for interpreting a model fit as well. But again, please go ahead and watch these videos on your own time. All right, again, we'll just review, we'll just scroll through the lab here because I want to get to the King's House Price Lab. So here we're back in our laptops and we want to start building out linear regression models with polynomial features and then evaluating them based on their residuals. So similar idea here. Here we're building a very basic linear model. We are using CPU to predict price. We already know this isn't going to be a great model because we know the correlation is fairly low. But either way, we can train the model, build it, and look at it. We got some interesting plots here. These aren't probably my favorite types of plots, but we can see that our predictions are way off of actuality. But they're kind of in the ballpark, which is at least a good first stab. If we look at the R squared as a metric, we have a really low R squared of 0.13. Usually for R squared, you want that closer to 1. And then looking at the root mean squared error, this is like on average, we are off by $533. So if I predict your laptop is $1,000, it could be 1,500 or it could be 500. We have no idea. So that's a pretty big error range here. Typically, for predicting price, we don't want us to be off by a margin that high. Now we're going to do multiple linear regression. So we're going to add in multiple features here. And you'll see by adding in multiple features, we end up creating better models. Our model fit, our residuals are a lot closer to the actual price of the laptop. And if we look at the R squared, we've jumped up all the way to 0.5. So more than tripled just the one feature alone. And we've lowered our average error down to about 400. So now we're plus or minus $400 as a prediction, which is better than 533, but honestly still not great. And also, I feel like we systematically over predict. We're the blue line in our predictions, so we're typically more expensive than the actual laptop price on average. So that's the other thing too, like trying to understand the limitations of the model in terms of actual like biases. All right, so now we can start adding in polynomial features. So we can start adding in our x squared, x cubed, etc. Again, you can see here we're just plotting different like curvatures. When we just have a linear regression, it's typically a straight line, but there's no reason why a linear model can't also have some polynomial or quadratic features and curves to it as well. And we do see adding in that x squared and adding in an x cubed or x to the fifth, we do start modeling the true price a little bit better here. So we're capturing nonlinear effects. And you'll see that here in this cell. This is a pretty interesting cell to me. We're still only using CPU, right? So if we just use CPU, we already showed that the R squared of that is pretty low at 0.13. But by adding in cubes and fifth degrees, we actually increase our R squared. So we get better predictions. We get more closer to reality by adding in those more complex polynomial, I guess, features. Typically, how this all works in real machine learning or predictive analytics pipelines is to shove everything into a pipeline. So here we are going to be taking our input data, scaling it, adding in our polynomial features up to a fifth degree, and then adding in a linear regression model for it. And when we run this pipeline, we should be able to get this model, and we've increased our R squared all the way up to 0.808. And I think this is with all of our original features, right? Yeah, there we go. We're fitting in our oh, where are we grabbing Z from? I think that was up here, right? Yeah, there we go. So Z is our multi-regression with all of these features. So we're taking so we're using all of those multi-features with the polynomial. So just by including the polynomial features, we've gone from zero point 0.5 up to zero point 0.8, and we've lowered our RMSE to $250. So we're plus or minus 250, which is more than a 100%, like a 50% increase on how bad our error was originally with just CPU. So pretty cool. Again, linear models, we're all still dealing with modeling and linear equations and mathematical equations. So it's also pretty explainable and easy for the computer to do. And we were able, just by a little bit of tuning with our polynomial features, multi-features, we were able to get something pretty good on the outside. So pretty awesome. Again, we got another forum post here in 7.6 or 7.7. So again, pretty interesting things here. Mostly like what do you need to think about when building a model? How do you evaluate models in the real world? Again, my biggest ones is garbage in, garbage out, right? Use variables that actually correlate and explain the target. Using the color of the car is not going to be a useful column, right? That's where EDA comes in. Look for those patterns, look for those relationships, etc. There's more advanced ways to evaluate your models, and yeah, choose sensible features, check assumptions, and make sure the model works in the real world. If we don't just make linear models in a vacuum, there's usually some reason to do it, right? So just make sure you're all aligned with the business value of the products you're creating. All right, let's pop on down to model evaluation. We'll fly through some of this stuff and then get to our keynote notebook, review the quiz, and call it a lecture. All right, so model evaluation here, some things to keep in mind. We talked a lot about noise. When you train models, your models can react to noise if you haven't done good feature selection. So common issues that you may see are what's going to be called over and underfitting. Overfitting is where your model finds patterns in the training data that don't actually exist in the real world. So it's fitting to noise, essentially, right? It's fitting to noise, not signal. Underfitting, you see this more often with like neural networks and things. This is mostly when a model has its training has been cut short. So it hasn't seen all the rows, it hasn't seen all the columns. It's underfitting the target on all the training data that it actually has at its disposal. So this just means increasing the training time, increasing the data size, increasing the number of rows or columns available, right? Just give the model more so it fits everything. Other ones to talk about here. One of the problems with linear regression is that it has assumptions, because again, it's math, and math always has problems, or math always has like requirements. So one of the big ones for linear regression is no multicollinearity. Essentially, this means that all your input features are independent and there's no correlation between them. This is usually not the case, and you even saw with our laptop one that that's not the case there. Like if I have higher CPU, I may also have more RAM. That just may be correlation with our independent features, right? So when you do have a lot of multicollinearity and you still want to be doing linear models, a quick and easy hack is just to replace linear regression with ridge or lasso. In our lecture, we're going to go with ridge. It's a good way to basically it has some work that it does behind the scenes to limit the impact of multicollinearity. Basically, it'll drive some of the useless features or multi-correlated features down to zero so they don't impact the model quite as much. So we'll see how that works in kind of our example here with the housing activity. And then finally, ridge regression does take in a what's called a hyperparameter, some kind of input that can change, and you get a different model if you choose alpha of 0 or alpha of 10, even if the data set is the same. So we can do what's called a grid search, basically try a whole bunch of these hyperparameters, iterate, and just let it run overnight and just see kind of which combination of hyperparameters does the best work on the model. Let's see. We'll quickly scroll through the laptop model, the laptop notebook for this, and then we'll dive into our final notebook. I'm thinking I'm a little bit behind on time actually now. So yeah, again, same library here. We have our laptops. We're building predictions against price. And here, note that as we start doing cross-validation and overfitting and things, we do see that our model does get worse as we start adding more useless features to the model. That's overfitting here. Ridge regression, we'll do this in our notebook as well. Notice here, this is where we do our grid search. We're trying a whole bunch of different alphas from 0 to 1 or to 10, basically. We're going to fit a whole bunch of them and see how they do. And we should be able to find kind of the best training score. And yeah, it looks like we do find a peak here with an alpha of about 0.01 or something. So yeah, same idea with the grid search, does the exact same thing. So I'm flying here. And we see here that by doing our grid search, we get the best model at 0.30. Notice we haven't incorporated scaling or polynomials here. We're just trying and talking about tuning more advanced linear models with hyperparameters. All right, let's dive into the main notebook here because I only have about 10, 15 minutes left. One more discussion post, probably worth thinking about. This is 7.9. What are the risks and limitations of models and things? So again, like my use case, you typically need to look at a holistic view of your model. Just because one thing tells your model is good doesn't mean it actually is good. That's why you should have that domain expertise in the models and data sets you create to be able to ensure that it's driving value. Look at multiple things and test on live data before rolling something out into production. Do we push to prod on a Friday? No. Do we test in production? Not always. So, same idea here. All right, let's tackle our keynote activity here. This is going to be kind of an end-to-end project. Let me spin up the environment while that goes. So it's a pretty cool one. It's real data. We have real housing prices from Seattle, Washington, in the United States over a 12-month period. And we want to see if we can predict the selling price of a house in this time period given things like square footage, number of bedrooms, size of the house, whether it's a waterfront property, all of that fun things. Note that this is a problem with machine learning and predictive analytics, though, is that this model is only worthwhile if you're trying to sell a house a decade ago. Would I use this model to price a house in 2026? Of course not, right? That we have what's called data drift. Data has drifted, prices of houses have skyrocketed. There's a lot of differences between how much a house was for a decade ago versus what it costs now. So you gotta keep that in mind too as you start playing around with these with models in the real world too, right? Like just kind of make sure that you're training data on relevant data to the current environment of your systems. All right, should be good to go here. We have a data dictionary breakdown of all of these different columns here. Let's go ahead and do our installs and get our data. Again, we're just going to fetch this housing data set and read it into our data frame. And let's start back and remember the very basic things we started this lecture on. We're going to start with pre-processing and data wrangling. We're going to go into exploratory data analysis, looking at distributions, outliers, and patterns and relationships. Then we'll move into linear modeling, where we're going to try both single, multi, polynomial regression, and linear and versus ridge. And hopefully we get some good prediction that we can take out of this. I know it's a heavy notebook. I know it's a heavy week. A lot of the stuff we could have much more targeted depth on, but it is what it is. All right, let's keep going here. Let's look at our .info. Again, this is where we're examining the health of the data. So again, remember the things we're looking for. We're looking for null values, we're looking for bad column names, and we're looking for bad data types. So in my case, I see three things. On the null values, we have null values in two of our columns, bedrooms and bathrooms. We have this unnamed 0 column, but we already have an ID column, so we could probably drop this one. So we have an irrelevant column. And then the data types, everything looks pretty good except for date. Date is a string. At the very least, it should be a date time. And then maybe we can extract like the month of the year. Maybe month could be an impactful feature in our model. So we got to fix our null values, drop the useless column, and fix our data type. So pretty standard thing here. Note that max we have like 13 or 16 missing rows, but that is less than half of 1% of all of my data. So it's really not a lot. I would probably just drop the rows in the real world, but we'll impute them just for the exercise here today. Looking at our ranges, this is worth just a quick glance. Notice that we have some crazy stuff. Like one of the houses has 33 bedrooms. But either way, if we start looking at our ranges, we go from 0 to 1, 0 to 5, but then we have some crazy stuff in square footage where we have a max range of 13,000, 4,000, 9,000. So I would say that normalization is probably going to be good here. We should normalize our numeric features into a standard range. So scaling will likely help for linear modeling is my conclusion. All right, let's do our data preprocessing. First thing we're going to do is we're going to drop the useless columns. I'm also dropping the ID column here just because I don't want to get them mixed up in my feature set for the modeling purposes. But usually you would keep the ID column just so you have a reference back to the original data source. Here are the null values that we have. Both of these to me are categories, so we should be using a median instead of an average, or the mode, I guess, the most frequent. So bedrooms, we should probably fill it in with 3. Notice that the average is 3.3, but you can't have a third of a bedroom. So we're going to fill it in with the mode, and we should be good to go. Same thing for bathrooms. Our mode for bathrooms was 2.5 bath. So that's what we filled in our null values as well. For quick recap, we have 0 null values anymore, so hooray. Let's cast datetime to an actual datetime object. And if I do my .info, everything should be good now. No more useless columns, no more null values, and all my data types look correct. As a quick feature engineer process, let's extract the month so we can use the month as a feature in our modeling if we wanted to. All right, let's do some EDA. What we're going to do here is we're going to look at some groupings, look at some distributions, maybe see if different features have patterns and relationships. Floors look pretty good. Most of our houses are 1 to 2 floors. A few of them are 3 floors. Maybe that's an attic or a basement for the extra half of a floor, right? We're going to look at distributions of waterfront houses versus price. I like looking at violin plots more than box plots, but they both tell the same story. In our case here, waterfront properties being 1 do seem to be on average a little bit more expensive than houses not on the water. But there's plenty of outliers here. There are plenty of houses not on the water that also cost a lot of money. So waterfront isn't going to be our only predictor of price. We can start looking at regressions or our line of best fit, looking at our correlations, especially looking at square foot to price. We see a strong correlation there. We can actually grab its specific number. This is what square foot living. Yeah, square foot living has a correlation of zero point 0.7. So that's really high. But it makes sense, right? The bigger the house, the bigger the square footage area of the living space, the more expensive the house is going to be able to sell for. Other strong features here, grade, square foot above, square foot living, etc. One other thing just to point out is there is multi-correlation here. So if we look at these things, like I bet you there's a relationship between the square footage of the basement and the square footage of the living space, right? And we can actually see that the square footage of the living space has strong multi-correlations to the number of bathrooms, the number of bedrooms, the square foot above ground, right? The square foot, or like the square footage of the basement. So we do have multicollinearity here, which means we technically do violate that original assumption of linear modeling. Let's put out a model. We're going to use longitude here. So I don't know why they picked longitude. Longitude doesn't have a correlation to price. So by definition, this is going to make a bad model. And wow, it creates a bad model. Shocker. Let's try with square foot living instead, and we end up with an R squared value of 0.49. Fun fact, the relationship here is that that is literally just the squared of the original correlation. So if we take this correlation of 0.702 and square it, it should give us that exact same value. Yep, 49285. The rest of these numbers are different just because of rounding. All right, let's do a real work here. Let's start with a multi-linear regression model. So these are my multi-features that I want to use. Floors, waterfront, latitude, bedrooms, square footage, view, bathrooms, square foot, grade, square foot. So we know we already have multi-correlation here. But if I build my model, we end up with an R squared value of 0.65, which is really good, actually. That's not bad. But again, what I wanted to show is that we definitely have multi-correlation here. And that is going to bias our model. So let's see if we can fix our model. Let's do some of the cool work that I said was good. Let's add in a scalar. Let's add in some polynomial features, and we'll stick with a linear regression for now. So the scalar should fix our ranges. Notice by default, this is going to only be adding a squared term, so we're not going to cubes or anything, but I'll leave that as an exercise for the listener. Let's go ahead and create our pipeline and refit our model. So look at that, it's beautiful. By only doing a scalar and adding in a squared polynomial feature, we've gone from a 0.65 to a 0.75. Crazy. So really good work to us. We're doing pretty good. Note that we do still have multi-correlation here. So there may be some overfitting happening in the model. Let's go ahead and try a ridge regression. Yeah, this was not with a train test split either. So that's not what we're going to do. We're going to do a train test split here. We're going to withhold some data that the model hasn't seen yet. And now we're going to go ahead and train a ridge model. As you know, ridge should hopefully diminish the impact of some of that multi-correlation. We're hard coding in an alpha of 0.01, but we could add that to a grid search. And notice without a scalar and without polynomial features, we're a little bit worse than the linear regression at a 648, but I say this model is going to be more trustworthy because we're no longer impacted by that multi-correlation. So same dealio, let's add in the polynomial features, and we see that we've improved to a 0.701. And now let's add in everything, including the scalar. And now we're going to go scalar, polynomial, and ridge. And if we do that, we should see that we've improved this as well up to a 0.711. So this still doesn't match the linear regression, but I would say that's because we did not do a train test split on the linear regression, and the linear regression was also overfitting due to its multi-correlation bias in the training features. There we go. I think that's the full notebook. Note that you don't have to do any of these screenshots or anything, but I do recommend saving and downloading the notebooks just so you have them for your own backup. So pretty good project here. We went from a raw, dirty, real-world data sets, cleaned it up, fixed our data types, did some feature engineering work, all that stuff, and then ended up creating some exploratory data analysis visualizations and linear models, evaluated those linear models, and selected our best pipeline. So pretty good work. Great job, class. All right, let's wrap up here with with the quiz and my big ideas, and we'll get you out of here. I know we're about at an hour already. All right, so let's dive into the quiz. Only 10 questions. We can fly. Question one, what does the following line of code do? It assigns a linear regression model. It doesn't, I guess maybe it's B. It creates a linear regression object and stores it. It doesn't fit anything and it doesn't predict anything. A is worded weird, but we're looking for the best answer. So B is the best answer here. What's the maximum R squared you can get is a 1. R squared is 0 and 1. What does this pipeline do? We do a scalar and then we do a linear regression. No polynomials, no correlations. It does do a prediction. It doesn't calculate the R squared value, um, but it does do a prediction. So I think it's C. What's the order of a polynomial created with this code? It's going to create your single, so your x to the first power and x to the second. So it's a maximum of 2. It doesn't do 0. That's like not really a thing. That's like just your constant. It's not a minimum of 2, and it's not 2 itself. It'll do both x to the first and x squared. So it should be a maximum of 2 there. Y represents our target variable. The result of this, cross-validate predict. So we're going to be predicting something. It's not going to be performing out of sample. It's not the average R squared of 2 folds. It's doing 3 folds anyway. The predicted values of a test set using cross-validation, I guess that sounds best. And I don't even know what a free parameter alpha. That's a ridge regression thing. So best answer here is C. How do you organize this for a grid search? Parameter is going to be my hyperparameter and then its values. So we don't need ridge yet. Alpha is not a function, and we can't just give it a list. It needs to know the name of the parameter as well. So B is the only answer here. Divide a data set, create a model, find the R squared value, add in a whole bunch of polynomials, and find the new value is 0.99. So some crazy things here. 100th order exponent is crazy. That is crazy. So they're way overfitting, doing some crazy stuff here. So what should we do next? Create another linear model. They already created 2 models. You should use the simpler model. Not always. If the 100th order does work, then it's fine. Is the 100th order only going to work on the rest of your data? That is not guaranteed. Or either, I think we'll be vague here and go with A, that you should just test the model further. So we'll go with A there. What's the purpose of folding? Foldings are used in cross-validation. Essentially, they allow you to remove biases of a train test split out of your model training workloads. And then here's our ridge regression, I think, whatever it's showing. What is true about oh no, overfitting. What is true about the model? The model is overfit. As you see here, it finds patterns in the blue curve that don't actually exist in the real world. So it's finding patterns that aren't actually there, which means it's overfitting. It's not a good fit, it's not underfit, it's overfitting to our training set. All right, let's see how we do. Submit all and finish. And hopefully, oh, we got 9 out of 10. Which one did we miss? Oh my God, is this just 2? I wonder if it just wanted 2 there. Dumb question. I guess the order polynomial, I guess it just wanted it to be 2. whatever. You can always retake the quiz. You have 5 attempts, so you can retake it as many times as you want, and try out different answers for ones that you miss. Or if you're happy with the 9 out of 10, take it and leave it. If you do have issues with the grades of quizzes, you can always reach out to me and I can change them on my own. All right, let's see. I got my big idea lecture notes here for module 7. You can also find them in my GitHub already as like big ideas or even in the README itself. So definitely a good thing to review at a high level. Big idea here, core analytical workflows of analyzing data and building predictive models. We used all these libraries today. We did all this work, missing values, inconsistent formats, dealing with categories, trying to find noise and outliers. How do we go from raw data to insights and analytics to predictive models to actually downstream decision making? Important part of being an analyst is to understand your data, understand the inputs, the outputs, what you're trying to do, understand how to wrangle and deal with bad data. Like we spent a lot of that earlier today. We can do EDA, make visualizations, look at the shape of data. Again, we want to know the health and biases of any of our potential features, both features for modeling as well as features for visualization and business intelligence. You don't want to have a dashboard in Tableau or Power BI with bad data that's underpinning it either, right? So we talked about all this work, looking at correlations, looking for relationships. Then we introduced creating models, what features and targets are, building out simple linear models, adding in polynomial features for nonlinear effects, and some curvature, bundling everything up into pipelines, and then evaluating our model on a predicted versus actual plot, mean squared error, and R squared. Sweet. We talked about overfitting, underfitting, and ridge regression, expanding our linear modeling tool belt, and then packaging all up together. So good stuff on that housing project in Seattle. Key takeaways here. Garbage in, garbage out. Always focus on data pre-processing to get your data ready for downstream analytics. Always do EDA before you do downstream consumption targets, whether it's a model or a dashboard. Understand relationships, patterns, and limitations of your data. Linear models, specifically regression models, are good ways to build some predictive power out of variables that have relationships. Evaluate your models, use R squared MSE, look at test data, unseen data. Make sure that you are able to model and estimate real world performance. And you have some advanced techniques such as ridge regression to help prevent overfitting, especially when you're violating linear model assumptions. How do we go from raw data, data analytics and analysis to models, predictions, dashboards, and decisions? Good stuff here in week 7. Week 8, quick preview. We'll be doing a deep dive into visualizations, data apps, and dashboards. So we'll be creating static visualizations in Matplotlib and Seaborn for slide decks and things. We'll be creating interactive graphs with Plotly and then interactive data apps and dashboard design with the Dash framework. So it should be a fun week. Notice that a lot of the concepts translate really well over to Power BI or Looker or Tableau, even if we're going to be using open source code-based dashboarding tools next week. All right, I think that's all I have. Thanks, everybody. I will upload this to our forum Zoom as well as to my YouTube later today. Hopefully, I will see you all in the forums for week 7 or week 8. And otherwise, I will see you next Tuesday at the same time for our week 8 live session. Don't forget that you can catch the week 6 and week 5 lectures already, either on YouTube or on Zoom. And I'll be backloading the week 4 lecture here in the next week as well. All right. Thanks, everybody. Enjoy the rest of your week, and I will see you all in the next one. Thanks, everybody. Take care.